Hey everyone, welcome to this next video on acids and bases, where we're going to start talking about more how they look in organic chemistry, how to identify them by functional groups, and how we can start to compare them based on pKa. So to start with, we are just going to have to get a little bit more of a diverse eye when it comes to identifying acids and bases, because in organic chemistry, they're going to look different than something that's just HCl or HBr or HI. They're going to come in a lot more different forms. And that's not to say that we won't use those acids, but we're going to have to identify other ones as well. So I'm going to start off talking about acids. We'll talk a little bit about bases, but this is going to be more acid focused. Any hydrogen, essentially anywhere, can be acidic, but we kind of have to just qualify and compare. So any hydrogen atom on any of our molecules maybe is an acidic hydrogen. When we're talking about an acid-base reaction, we're only going to react with the absolute most acidic hydrogen. So we have to figure out which one is the top, which one is most acidic. So a couple of examples of things that may be obvious, maybe not so much. Here are two organic molecules. If we're comparing them to one another to say, pick out the most acidic proton on each of these molecules. Well, this first one, who knows, you may already know what this is. It may seem obvious to you that there's already, this hydrogen right here is drawn out for us. That must mean it's important for some reason, right? So yeah, that one could be the most acidic, and it turns out that it is for this example, but there are other hydrogens here that we can't forget about, right? So those may be important to consider later on, especially if we look at this other example here on the other side. Now there's no hydrogens here whatsoever for us to say, oh, that's the obvious one. We'd have to think about each of the individual types of hydrogens, where they are, and therefore how that changes their acidity. So we want to look at a few of the most common acidic functional groups, because these will be patterns that you're going to start to recognize, because you're going to see them over and over and over again. When you see that functional group, you know, okay, that's pretty acidic or mildly acidic in your brain. So to just go over really quick what a functional group is, you may or may not have heard this terminology before, but a functional group is just some kind of a small chemical motif. And what is a motif? A motif can be anything. It can be like a pattern in design. In this case, it's just going to be a small combination of atoms arranged in a specific way. The other thing that I would compare this to is, you could say, even just language, words, right, and letters. If you were to take the alphabet is a collection of 26, in the case of the English language, 26 different letter motifs that you can rearrange in different ways to make words that have different properties. So same thing with molecules. If you take functional groups and you combine them together in different orders in different ways, you get molecules with different properties. So that said, let's look at some structural motifs that are acidic and start to introduce some of their names. This first one here is the one that we saw earlier in that first example, and that is a carboxylic acid. And so the key there is in the name of this one. It's an acid, so of course it's going to be acidic, right? The actual part that is the carboxylic acid is this part here that I'm going to box in blue. To have a carboxylic acid, you have to have this carbon-oxygen double bond here, which is also single bonded to an OH group. That is what constitutes a carboxylic acid. Anything that's out on this end over here doesn't matter. It doesn't change the fact that this part is a carboxylic acid. Okay, next we have alcohols. So these may look like a pretty familiar functional group that we saw probably a little bit in Gen Chem, but if not, the alcohol part of this motif is just this bit here, where an OH is covalently bonded to something else over here. That's supposed to be a question mark, so anything outside of that box doesn't change the fact that this is an alcohol. So that proton there is relatively acidic for an alcohol. And again, since we already looked at this, I forgot to mention that that sort of squiggly underlined proton on our carboxylic acids is the most acidic. And then last but certainly not least, we have sort of a quasi-functional group, I'm going to say this is a protonated oxygen. So this, what I've drawn here, if you especially compare it back to the previous example, is a protonated version of an alcohol. So this is really to say that anytime you have a positively charged oxygen, there are going to be many different functional groups that have different names. But if you have an oxygen with a plus charge on it, it doesn't like to be positively charged. So if it has hydrogens on it that it can get rid of, those are going to be very strongly acidic. So these two are the kind of more traditional functional groups, and this one is something that is kind of a modification of other existing functional groups. We'll start to see these more as we look at some examples. So next, let's think about some bases. As I said, this is going to be acid focused, but there are definitely some base things that you will need to know for organic chemistry. So we talked about, protons and identifying most acidic protons. And so the proton is something that gets given up by an acid. A base needs to accept a proton, and so it has to do that with some electrons. So any lone pair electrons could potentially be basic. Again, you may have to rank them and decide, oh, okay, if I have multiple, which one is the most basic? So a couple of common functional groups that have lone pairs of electrons available to them are amines, or anything that has this NH2 format to it. It may not always have two hydrogens on it. You may see it have two carbon groups like this, where it only then has one hydrogen, or maybe even all three carbon groups and no hydrogen. But the most essential part is that this lone pair on any of these is going to be a good, solid organic base. The other example are kind of in opposition to that last example for the acids side, anything that has a negative charge, right? So this is the conjugate base of an alcohol. This negative charged species is not super happy, so it's ready to go out and pick up a proton from some acid species. So basically anything with a negative charge can act as a base. Commonly it will be oxygen, but you will also see carbon and nitrogen as well, acting as bases when they are negatively charged. So we've talked a lot about oxygen-based things, whether that's oxygens with hydrogens on them or the lone pairs on an oxygen acting as a base. What about carbon? What's going on there? We said in the intro that that's the point of organic chemistry, is it's carbon and hydrogen. So where do those kind of fit in this acid-base scheme? Well, a hydrogen that's attached to a carbon can be acidic, but it kind of depends. So the location of that hydrogen and the functional groups around it are going to determine the strength of that acid. And so there's a lot of different ways that carbon and hydrogen can hang out together. So this is where our friend pKa comes back. So our pKa values will tell us the relative strength of acids. So this follows some golf rules. We're going to use some numbers here in the next couple of slides, but the thing to remember is that pKa goes by golf rules, that lower numbers are going to be stronger golfers, acids. Okay, so let's take a look at some pKa values that are going to be good to have just kind of tucked away in your brain. You don't have to memorize these right off the top. But I think it will be good to commit these. I think there's just 10 values here, so not too many, to commit these to memory just for the sake of speed, mostly. So here's my sort of gradient of different pKa values. So let's set this up. We have at the left-hand side of the page here, things that have high pKa values. And that means that they're really not going to be strong acids. They're going to be very weak acids. Let's spell that right. Weak acids. There we go. Whereas at the other side, we're going to have very, very low pKa values. But that makes them really, really strong acids. So let's fill in some numbers here to give you some ideas. Most of these I've sort of truncated off in units of 5 or 10. So hopefully they'll be easy enough for you to stick in your mind and remember later on. So a lot of these are hybridization dependent. So that's going to be a big factor as far as make sure you can recognize your different hybridizations and remember where they are on this pKa scale. So if we have our pretty standard sp3ch hydrogens, that's kind of the bread and butter, the building blocks of so much organic chemistry. They're not very good acids. They'd rather just be the way that they are. So they're coming in at about 50 pKa. These are all going to be approximate values, but they're good enough values for our purposes. Now, if we change the hybridization and go to an sp2ch, that makes them a little bit more acidic, clocking in around 45. If we go to nitrogen, there's a difference between carbon and nitrogen in electronegativity, so that makes NH protons more acidic. They're around 35 pKa. And then if we change the hybridization of carbon yet again to sp, that goes all the way down to 25. Now we start to see some of these oxygens that were in the common acidic functional groups that we talked about before. So an sp3 oxygen, fairly acidic, that clocks in around 15 pKa. If we have a nitrogen that's protonated, now, that nitrogen doesn't necessarily want to have that positive charge there, so it's more acidic than the neutral sp3 version that we looked at earlier. So this is about 10 pKa. Here's our friend, the carboxylic acid from before, and this specific structure, the structure of all carboxylic acids that I've used in this presentation so far, is specifically acetic acid, which is the exact same thing that's in any household vinegar that you use for eating or cleaning. And that clocks in around 5 pKa. This is a fairly strong organic acid. And then we have a few more. Now, these ones down here, you'll notice by their formulas, do not have any carbon in them, so they're not organic acids per se. But we know that these are kind of more the strong acids that we learned about in Gen Chem. So we want to have these values tucked away as well so that we can compare the other organic acids that we're going to be looking at. So H3O plus, again, fairly strong acid. Now we've crossed over and gone into negative numbers. That's actually at a -2 pKa. H2SO4, sulfuric acid, is fairly similar at about -3. And things like HCl, HBr, HI are really, really strong. So they're going to be close to -10 pKa. And they vary a little bit between the different halogens, but -10 is a good baseline benchmark value for us to get started with. So there we have some values as far as pKa. Again, committing these to memory slowly over the course of this unit will be a good idea, just again, for speed. So some of these functional groups you may not super be familiar with. That's okay. You don't have to have all the names down or anything like that. We just want to start recognizing these functional groups. So use this sheet as a way to practice with the different acid-base type reactions that we're going to be learning about next. So I want to introduce you to my absolute favorite acid-base type of question that you will get on your homework. And you can't see because the video is not on, but I'm winking. This will probably be on your exam, hint, hint. So I want to just go through the structure of how this question works and practice through an example with you so that you get the idea of how it goes. So you will be given something that looks like this. You'll be given an acid and a base. You'll know what their identities are, or maybe they won't be that familiar to you. We'll see. And then you're going to have to tell me what the products are. So you're going to have to show the structure of the conjugate acid and the conjugate base. We also have this mysterious box here in the middle. Talk about what that is for in a second. So first things first, I'm going to ask you to redraw whatever the structure of A and B are and show me how that acid-base proton transfer occurs. So we'll practice through all of these steps in a second. The reason that I want you to redraw A and B is just for practice drawing to make sure that you're identifying all the parts of the structure. So the second step here is going to be, oops, oh, I'm giving it all away. Secrets, okay. There we go, pardon the scrolling. You're going to then draw in the products of the reactions, like I said, the conjugate acid and base. Then you're going to add the correct type of arrow. So we're not sure what type of arrow goes here. You're going to add that into the box. And then last but not least, you're going to list a factor that helped you come to the conclusion about this arrow here. So don't worry about step 4 yet. That's something that we're going to talk about in the next lecture. So hang on to that for now. Let's do an example 1 together. So I've given you some kind of an acid and a base here. We have to figure out what the conjugate acid and base are and show how that proton transfer occurs. So normally you would redraw these two species, and actually I think I will, just for the purposes of drawing out all of these bonds very explicitly. So sodium here, spoiler alert, is going to be a spectator ion, so I'm actually not going to draw that one out again. You will have to though, so don't do as I say, not as I do. And then here's H3O plus, but we're going to draw out all of these bonds explicitly. And I'll put in a lone pair just to make it a perfectly good Lewis structure. So a good place to start is to identify acid and base, right? So this may or may not look familiar to you, something that we talked about earlier, but if we go in and say, okay, which one of these two species has protons that it can give up? Hopefully we're not looking at this and saying, yep, that looks like an acid. It's just a chlorine atom, nothing else. It has no protons, so that can't be the acid. This must be our acid. So feel free to label these. In fact, I will recommend that you do that this is our base and this is our acid. So now we have to come to what are the products of this reaction going to be? So it kind of depends if you want to, we're going to talk about arrows in a second. If you want to do arrows first, that's totally okay. But for now, I think it may be easiest for us to just say, okay, what would change about this structure here of this H3O plus if we removed a proton and put it onto this Cl? So without drawing any arrows, we're just going to say, okay, if the Cl picks up a hydrogen, it'll look like that. And then if the H3O plus lost one, we would still have two. This lone pair would still be there, and we will have regained another lone pair. We'll show how that works in a second, to make water. So these are going to be our products here of this reaction. So thinking about these, we also want to give these labels, right? Remember, as conjugate acid and base. So our base turned into the conjugate acid, and our acid turned into the conjugate base. So our HCl here is the conjugate acid and water is the conjugate base. So let me get rid of these arcs to make it a little bit nicer and cleaner looking. So now we know what the products are, and we just want to show how we got there. So this will be maybe your first introduction to what we call arrow pushing. You may hear it called curly arrow pushing. It's the way that we show electron flow in organic chemistry, and it is really big and really important. So this is kind of the training wheels version that we're going to practice on acid and base. There will be a lot more to come on this later. So when we do arrow pushing in an acid-base reaction, what we're trying to show is how the base picks up the proton. And this can be a little bit confusing to some students, so I want to just clarify that arrow pushing is really just here to show the motion of electrons. It's not about picking up atoms and moving them. It's about showing how the electrons flow through a chemical reaction. So you are always going to start with the electrons and go to a target. Well, again, more on this later, but for the purposes of acid-base chemistry, we always want to start with our base and go toward our acid. So I put this lone pair in kind of a weird spot just because that negative charge is in the way. But I'm going to start with a lone pair of electrons from our base. And in fact, I'm going to actually recolor over these ones for emphasis with red. They are going to reach out, and those electrons are what are going to do the picking up of the proton. So we start here with these red electrons, and they reach out and they grab one of these hydrogens. Doesn't really matter which one, right? But this is the one that sort of ends up missing in the product, so we're going to pick that one. Okay, so that's what's happening when we reform a H to Cl bond there. So I've highlighted that in red to show that the red electrons made that new red bond. Then if we think about what's happening with our water, that's a little bit different because, excuse me, we're not grabbing anything in particular, right? The base is reaching out to grab a proton, but what's going on with the water? The only difference, right, is that it's missing that proton in the product here, but it's also got a new lone pair of electrons. So where does this lone pair of electrons come from? It comes from this oxygen-hydrogen bond. So I've drawn in two little dots there on that bond to represent that's what they are. It's a pair of two electrons is what forms that bond. So when we break it, those two electrons have to go somewhere. They need a new place to live. So they actually just go and hang out with the oxygen instead of being shared between the oxygen and the hydrogen. And we represent that by drawing those two electrons as kind of just going back over to the oxygen. And that's, again, where that blue lone pair comes from. A couple other quick notes on arrows. You'll see hopefully that I've made it pretty clear. Any curly headed arrows should have kind of a double headed arrow at the end. If you draw something like this with kind of the harpoon, that means something different. So we may come to that later on. So this is just a brief introduction on how to show the motion of electrons using arrows. Okay, back to the question at hand. We now need to start thinking about, gee, what goes into this box here that I'm drawing underneath somehow, not exactly sure how that happened, but we need to put an arrow for this reaction in that box. And it has to either go forward all the way, backward all the way, or it has to kind of equilibrate between the two. In order to decide that, we need to know a little something about acid strength. So we need to compare the pKa values of our acids to see which one is stronger. So if we think back to our benchmark values from previously, if we are looking at our original acid here, that was H3O plus, and that has a pKa value of -2, whereas our HCl conjugate acid that we made is going to be somewhere on the order of -10. So now we know which side has the stronger acid. It's the product side here. But what does that tell us about arrow direction? Some of you may remember a little bit about this from Gen Chem as far as how we want to move related to the strongest acid. But I wanted to introduce to maybe a different way to think about it that's a little bit more mathematical in a very simple and easy way, because you know I'm all about easy math. So before we get there, I do just want to say quickly that I've focused here on comparing the acids, so the conjugate acid to the acid. If for whatever reason it makes more sense in your brain to compare the bases, that is definitely a very totally good, valid way to go about it. I'm just not going to cover it in these lectures. So please reach out and say, oh, you know, Grace, I'm not really understanding the acid side. I want to try the base side, and then we'll talk about it. So in order to figure out what arrow type we want, I want to look at what we call the delta pKa. So doing this simple delta or difference between the two pKa values is going to tell us the arrow type. This is a really useful tool if you know the pKa's for your acid. So what is delta pKa? This is just like any other delta that you've encountered in chemistry and probably a lot of other fields, but it just means the difference between. So we are going to take the pKa value of whatever our product is. So in the case of acid-base reactions, we're talking about the conjugate acid, subtracting the pKa of our reactant, or the original acid that we started with. So that's pretty simple. You just subtract the two, see what the difference is. And then based on the magnitude of that difference, it'll tell you which arrow type you want. So if the pKa is, in this first case here, somewhere between 0 and 6, that means that the acids are pretty close in strength, and that tells us that we are actually going to be in a situation of equilibrium. So I'm going to draw in our little equilibrium arrow here. So if you have a small delta pKa, let's not use any more arrows here than we have to. you want to use the equilibrium set of arrows. Now, on the other hand, if you have a very large delta pKa, anything bigger than 7, that tells you, yeah, one of these acids is way stronger than the other. So we want to then use this full on all the way or none of the way type of arrow. The other thing about this is that I said, yeah, it's got to go all the way either to the products or maybe it's going to go back toward the reactants. So this set of numbers here, let me give this a little highlight. So those two numbers are all about magnitude of delta pKa, but delta pKa can have either a positive sign or a negative sign. So when we talk about the actual sign, if it's a positive delta pKa, as far as the sign of whether it's positive 7 or negative 7, that tells us that the reaction is favored to go forward. That means that the products up here have a higher pKa and therefore are weaker acids. So a positive delta pKa tells us that the reaction is going to go only in the forward direction, like so. If the value of delta pKa is negative, then that tells you that actually the reactants were stronger than the products. So in that case, the reaction doesn't want to go forward, it instead wants to go backward. So based on the sign of delta pKa, you can tell which direction you want your full on arrow to point. So you kind of start from going your full reaction arrow versus your equilibrium arrow. And if you use the reaction arrow, then you need to say, okay, which direction does this reaction actually favor? And equilibriums, like I mentioned before, can be a little bit lopsided to favor one side over the other, but we're not going to focus a lot on that this semester. It's more going to be, does the reaction go all the way forward or all the way back in the case of a full conversion? Okay, so with that knowledge, let's go back here really quickly and do a little delta pKa analysis with our numbers. So our delta pKa is going to look like products minus reactants. So there's our negative 10 minus a negative 2. So that's negative 10 plus 2 equals negative 8. So because of that, we can say we're outside of that 0 to 6 range. This goes all the way one direction or the other. And because it is negative, it means that this must go all the way back toward the starting materials. Now, if you do this math and you're like, okay, I think I did the math right, but I still don't really know, we'll learn some tools in the next lecture to do a quick rationalization just to see if it makes sense. And even without those tools, we can do it for this example. Think about, this is HCl. It looks a little weird because it's drawn backwards, but it's HCl. That's a really strong acid. That's stomach acid, right? Water is really, not that strong as far as, I'm sorry, the conjugate acid of water here is not that strong compared to stomach acid. So it makes sense that we want to favor the side away from our strongest acid and going toward the weaker ones that we started off with. So again, there's some ways to go about doing a little bit of a rationalization to help check, okay, I came to this conclusion using these tools that Grace showed me, but do they actually make sense, sort of, logistically, common sense wise? Definitely always a good check to do. Okay, so there was a lot in this little mini lecture about what pKa's are and their values given to specific functional groups. And we also sort of walked through that type of practice problem that you will definitely see a lot more of this semester. And we introduced arrow drawing for the very first time today. Arrow drawing is one of the hallmarks of organic chemistry. So there is a lot of stuff here. So if you're feeling a little bit off, shaky, like you want more practice on it, please go back and review the things that are in this video. Watch it again if you need to. Definitely work on some practice problems. And then if you get to the point where you're feeling good about it, you can start looking ahead to the structure-acidity relationships that are going to help us use our brains in organic chemistry when we don't know pKa's, because that's probably going to be the case a lot more often than not. is that you won't know the pKa of something. So when we sort of look at the structure, we can tell how it's going to affect the acidity even when we don't have numbers to put to it. So there's a lot here. Keep practicing, keep working away at it, and definitely post in the discussion forum, email me, come hang out in office hours if you have any questions. Other than that, take care, and I'll see you in the next video.